Good afternoon, everyone. I hope you enjoyed your lunch. My name is Gary Egan. I'm a member of the math department here, and one of Rob Johnson's many helpers in putting this conference together. It's my pleasure to introduce Charlie Knauf from the Monroe County Environmental Health Lab. Charlie uses a lot of the statistics that we teach our students, and many statistics that we don't teach our students. He's going to share with us today some uses of regression in his lab, as well as a few other statistical methods that he uses on a regular basis. Present to you, Charlie Knauf.
Thank you very much. I traveled a very short distance. Our laboratory is right next to the college over here on Crittenden Boulevard, so I actually could have walked here. The Environmental Health Laboratory is a division of the Monroe County Health Department, and we are mostly involved in surface and groundwater quality monitoring. We also monitor occasionally food samples, although none of us particularly want to see food samples come in. They do once in a while. We did have an extensive blood lead monitoring program, which has been privatized in the last couple of years. We do a great deal of testing of drinking water and of streams and lakes and groundwater situations within Monroe County. And we're a fairly complete chemistry laboratory. We do a lot of nutrient monitoring. Nutrients in our business are things like nitrogen, phosphorus, which promote algal growth, which leads to eutrophication of water bodies. We do a lot of tracking of heavy metals, and we're in the process of expanding our capabilities so that we can monitor organics, such as polyaromatic hydrocarbons. In all of this monitoring, a lot of what we're doing is taking real-world samples which have unknown composition and measuring what is in those samples by comparison with known substances. And that's where we use regression. A second facet of statistics in our work is, and this comes up in industrial processes more and more and is being used all over the place, is tracking of the quality of our work, especially through measures of central tendency. And I will apologize to you up front, I am not a statistician. I have taken some statistics. I studied with Dr. Adicula down at SUNY Geneseo, so I did some educational statistics. And I've studied with Dr. Lanzafame in chemistry, the statistics here. But I am not a statistics professional, so some of this may be a little under your heads to begin with. But by way of introduction, I'm going to start out with just a little basic chemistry. This is a plot of what's called Beer's Law, the basics of Beer's Law. And Beer's Law is normally taught in terms of what's called atomic absorption, but is also applicable to a number of other phenomena in chemistry. And Beer's Law and other measuring methods used in chemistry depend on a relationship between the concentration of some substance, which is generally in solution. If we're dealing with a solid or a soil, which is a solid, we will generally put that substance into solution in order to measure it. And the normal solvent for our solutions is water, but certainly there are other measuring systems that could use other solvents. Hexane is very popular in organic analysis. But we look at the relationship between the concentration of a substance in a solution and some physical phenomena. And the physical phenomena are generally something that can be expressed in terms of radiation. And the most common kind of radiation you deal with is light. Probably the most common phenomena in terms of light that you deal with is color. The woman over here has an orange coat on, and we see that bright orange because a particular wavelength of light is being reflected and other wavelengths of light are being absorbed. And Beer's Law basically says that there's a relationship, A is equal to A, B, and C, where small a is an absorptivity, is a proportionality constant, and it is a constant in the relationship. B is the length of the path that the radiation travels through, and that's also a concentration. And C is the concentration of the analyte. Therefore, the absorbance of light, which can be expressed as a color, it can be expressed in a number of other ways, is proportional to the concentration of the analyte. This is limited. As you get up to the top of the relationship, it deviates from a linear relationship because the concentration of the substance becomes so dense that interactions between the molecules interfere. And at the bottom end, ionization occurs, so the concentration of the substance is so low that it's impossible to tell the difference between the response attributable to the substance and the noise generated in the measuring system. This is maybe a little bit convoluted, but it explains a little bit about where these linear relationships come from. The way that we employ a lot of this in terms of regressions then, my next sheet is a basic bench sheet for a nitrate analysis. NOx is oxides of nitrogen. And what we basically do is we make solutions of known concentration. So at the top of this particular plot are, in this column, what are called standards are 100, 200, 400, 800, 12, 16, and 2000. Those are, and then there's a 2000 for nitrite, which is also run usually at the same time as nitrate. And those are standard solutions that the technician at the bench prepares, generally from a salt, and then puts the salt into solution, and then pipettes from a known stock standard and dilutes to get known entities of standards. The things down along here are the unknown samples. And what we do is basically measure the height of a peak, and my next overhead goes to, in this case, we react the standards and the samples with particular other chemicals which cause the formation of a dye. A light beam is passed through the dye, and based on the concentration of the nitrite in the sample, a voltage is produced, which is then transferred to a strip chart recorder. And the strip chart recorder, the pen deflects based on the voltage, which is dependent on the concentration. And over here we have our standards, 100, 200, 400, 800, 12, 16, up to 2000. And you can see that there's almost a linear kind of a phenomenon going on just in the way that these, what we call peaks. This is a peak for a 100 standard, peak for a 200 standard. You can see the linear relationship there. Over here, we have our samples. So basically, in terms of the mathematics of what's going on, what we're doing is measuring the height of the peak. And we basically take a ruler and measure that on paper. Now, more modern systems, that voltage is fed into a digital integrator, and the digital integrator gives us a number, or feeds a computer program a number, and the regression is all done in the computer, and the value comes out. The older system, and this particular system, we're still doing manually, although we're in the process of automating it. We measure those peaks. And where we have our standard concentrations, you can see that the measurements, although they don't correspond one-to-one, show the same kind of linearity as the standards. And then our unknowns are measured down here, okay? And from that, we go to the use of the regression. So we isolate out the data, and what I'll do is move this down a little bit. We basically have measured our standards and our peak heights. And we look at the standard as the independent variable x in the relationship. The peak height is the dependent variable, the measured quantity in the relationship. And from that, we take this through regression. Now, at one time in a laboratory, when everybody carried their calculator in their pocket, and if they weren't careful, part of it went flying when it was a slide rule, the time that it took to do a regression necessitated use of a calibration curve that was run for a lot of these analysis once a month. And it was perfectly acceptable to the regulatory agencies that you did a calibration at the beginning of January and you didn't do another one until the beginning of February. Of course, the confidence in the data produced during that month was a lot lower than it is now. With the use of computers and the use of calculators, we do correlations at least at the beginning of every day, of every analytical run. And then when I get to quality, I can explain a little bit about going out of control. Anytime a system goes out of control, it's necessary to completely recalibrate it with a new regression before any data can be generated. But basically, the standard is the independent or x variable. The peak height, which we measure, is the dependent variable. They're both used in the regression to determine the slope and intercept of a best fit line. The slope and the intercept are then used to predict the concentration, what a lot of calculator buttons call X with a little X prime. The concentration of the samples based on measurements Y taken of each sample using the reverse of the line equation. Y minus B divided by M equals X. So the measured value minus the intercept divided by the slope gives you what the concentration of the original substance should be. For this to be done, the correlation, which this happens to be a Quattro Pro regression output, and it gives you R squared. R squared is actually the square of the R, the correlation that we're looking for. So we add the square root down here. We have to have a correlation in our work of at least 0.997, which in some work would be impossible to get, but in medicine is actually considered a fairly sloppy correlation. If the line does not meet 0.997, we got to run the standards again. It's not linear enough a relationship to work with. From that, one other thing that we can talk about, if we have samples that are outside the range of our standards, we can use dilution to bring them down into the range. And this is something that you can't do in population statistics or educational statistics. It's very hard to dilute bodies or counts. But if we have a substance where the peak goes off the scale of the chart, we can take that sample and add 50% sample, 50% distilled water, bring it down into the range, and then when we do the final calculation, we multiply by a factor of 2. If a 1-to-1 dilution still puts it off scale, we'll run to 4. We continue to dilute until we can get it into that linear range and analyze it. However, each time we do a dilution, we magnify the potential error in the result, so the confidence, the level of what we say plus or minus in a given result goes up as we go up through magnitudes. So a finished analytical sheet with all the data. Well, first of all, here's a plot of the data from there. And this is what was used up until the calculator and the micro computer came along. This would be plotted at the beginning of the month, and then we'd go along and we'd read our measured values on a Monday for our unknowns and come across a line to this line, plot down, and well, it's about 750. And the calculator gives us a lot better accuracy than the plot. But you can see here, too, that there is starting to be some deviation from linearity at the top of this plot, as would be predicted by Beer's law in this system. So having run those calculations, these spreadsheets are set up to have the line equation built right in here, and we get right into here, we get our values back. And looking at the standards and the peak heights, if 100 produces a 12.8, then a peak height of 7.5 from a linear relationship should produce about 53 units, concentration units. In this case, it's micrograms of nitrate per liter of solution. We do also round in the last step. There were no dilutions in this run, so the value times the dilution is the same as the value. But you can see that even though we've got 52.9, when we took what we knew was 100, we got back actually 99.5. In the case of what we knew was a 2000, we got back 2006. So 52.9 or 53 actually, as far as how we would express that to our customer in describing a sample, is 50. And in these, they tend to round to tens, in the tens and hundreds places. And that kind of takes care of the error. There are much more rigorous analyses of error that are used in chemistry, especially in research chemistry, but from an environmental standpoint, the error gets lumped into the, first of all, detection limit, less than 10 parts per billion. We're into that area that we don't trust the measuring system. And then as we go out, 1600 would probably be recorded 1600 plus or minus 100, whereas 570 is 570 plus or minus 10. And down in here, actually, we start to go to fives. We don't drop it to 1, 50 plus or minus 1. So this is the use of regression for measurement and calculation. A second thing, and what I'll do is I'll leave this up for a moment. There are some codes on here. The codes here identify samples, locations. There are some codes on here for what are called external quality control. ERA is a company known as Environmental Resource Associates, and in order to ensure the quality of our work, what we've got here now is we got a technician who says they made a solution that's 100 parts per billion. And the regression says, yeah, it's 100 parts per billion. But it might actually be 80 parts per billion, and it's real linear, and the regression still, you know, is off. The line's good. It's a good straight line, but there's no reason to believe that it's necessarily anchored at 100 and 1200 without measuring something that we know, something outside of what we put into the system that we know has a particular concentration. And that's where quality control comes in. We obtain samples from other companies that are assayed and certified to have a particular concentration. And we analyze those solutions, and if they are not within a particular set of limits, then we know that our work is not particularly accurate. We also do replicates of the unknowns that we run. And if those do not fall within particular ranges of each other, then we know that our work is not particularly precise. Thirdly, we analyze samples where we add an aliquot of what we're looking for to the sample and then see how much we get back of what we added. That's what's called spiking. And if we don't get good recovery there, then we know that there's a problem with what's called the matrix, the sample itself. There's something in the sample that's either boosting the response or masking the response. So in terms of accuracy, this is a pretty common chart for chemists to see. It's usually drawn as a dartboard. This is a little more simple. And I would think you all have seen something like this in terms of statistics. But the ideal work that we could do is right here. We have a situation where the work is extremely accurate and the work is extremely precise. Now we have a second situation here where the work is the measurements are extremely precise, but they're not particularly accurate. That's not a good situation. This is a situation where the work, or here's a situation where the precision is low and there's a lot of bias, and this is a situation where the accuracy is a little lower in terms of bias, but it's very imprecise. This is probably the worst situation you could have, and this is the ideal situation. And ways that we measure and track this are, as I said before, we analyze substances that are provided by an outside company and then compare those results with the results that we've achieved. And one problem that we face in that kind of a situation is that we get different concentrations from everyone. So in all this quality work, we do what's called normalization. And normalization allows us to compare different concentrations on the same chart or in the same system. So for an external, which is a sample prepared by someone else, we take the measured value, what we get, we divide by the true value, what they say it is, and that gives us a normalized value. That way, if I have a substance that ERA tells me is 200, I got 210. I have another substance they tell me is 600, I got 620. I'm comparing apples and oranges as long as I leave them in that numerical level, but if I divide the measured by the true, in each case I get a value that clusters around 1, that's normalized around 1, or it can be converted to a percentage by multiplying by 100. But I can compare the quality of both of those measurements directly by converting them to normalized values. For replicates, we take measurement 1 of the sample minus measurement 2 of the sample, and I should mention that's the absolute value of that. Negative signs drop out. We divide by the average of measurement 1 and average measurement 2, or the mean, and we get a normalized value. So the range between the samples divided by the mean is the normalized value. And with a recovery, we divide what we get as a recovery divided by the expected recovery, which would be 100%, and we normalize. Recovery I'm not going to spend a lot of time on. We accumulate these kinds of measurements over time. There it is. And we are required under state law in New York by the New York State Environmental Laboratory Approval Program to run charts of our quality. And this is a tally that's used for an external quality control chart. Basically, in this case, all the ERAs were the same, and there were only about 5-6 dates that these were run on. But these were the measured values and the true values. These are the normalized values. From this, we plot a chart which uses basic central tendency measurements, mean, plus or minus 1, 2, and 3 standard deviations. And this is a chart that's known in industry as a Schuhart chart. Has everybody heard that term? It's not that familiar a term yet. But an extremely useful tool. This is the Schuhart chart of nitrate for 1997. And the colors don't show up too well. There are some other lines on this that we're working with internally, some new quality programs we're doing. But basically, let me try moving this over a little bit. You're looking at the mean as the central point in the chart. Plus 1, plus 2, and plus 3 standard deviations. From a quality standpoint, we look at the region from 1 to 2 as the basically controlled region. And the 2 standard deviation point is what's called the warning limit. 3 standard deviation point is the control limit. And statistics tells us that 99-point-something% of our values should fall within that range. So anything that's out of that, we've definitely got a problem. 94% of our values should fall in here. So we start getting values in this region or down in this region, we may have a problem. So that's why this is a warning limit. And these are given dates, June 2nd, June 3rd, June 4th, June 6th. These are the results that were obtained. Now in this case, and I noticed this when I copied this, here's an out of control point. The normal process would be when that point got plotted, all the data from that run was rejected because this external, this was telling us our accuracy, is out of control. So the accuracy of everything else in that analytical run was out of control. So this run would have had to be repeated based on that point. Now, this is normalized. One thing that they do is look at the range it's in. If there was 2 samples that were, this was in a very high range of the analysis, getting up into that deviation from linearity and the regression, they may have just repeated the data that was in there. These other 3 points that are in control down here may have been in the lower range, and that the accuracy was good in that part of the run. On this particular day, 1 point is really pushing the upper warning limit, but there's still a fairly good distribution about the mean. But these charts are used to track quality over time. And I have another overhead coming up, which is used to show this, to demonstrate the kinds of bias that we can see in these. The second type of Schuhart chart is a duplicate analysis chart. And this comes straight from the New York State Codes, Rules, and Regulations, which dictates the statistics that must be employed in laboratories. Basically, for duplicate analysis, we calculate a range. We measure something once, we measure it twice, we get a range. We do the same thing, a tally of 20 points. Calculate the mean of that tally. That becomes the mean range. And then the upper control limit becomes 3.27 R. And 3.27 looks to me like the value from student T chart for a population of 2. Times the range, and the upper control limit becomes the point where we have to cut off in terms of acceptance of the precision of the run. And this is a tally for precision, same basic thing as you saw before, except that the limits up here are calculated a little bit differently than in terms of just straight central tendency. One thing in terms of central tendency is that because we're using the absolute value with precision chart, we don't have any negative area. So we're looking at 0, the average range of replicates, an upper warning limit, and an upper control limit. And again, as things get outside of the control limit, we have to redo the analysis. And this is a range chart, which this same kind of thing would be done used in industry for example, quality control measurement of gears have to be cut to a tolerance of a 10,000th. You measure 1, you measure 2, or 2 different people take a measurement, check that, and they could plot this kind of thing. And finally, we do the same thing for matrix. although I'm not going to get into this a whole lot, but this is another tally. And we plot limits around that centralized point again. And a similar chart for recoveries. And again, 3 standard deviations, 2 standard deviations, 1, the mean, and then the negative area. And what we're looking for, again, I'll emphasize this, is this kind of normal spread. You would expect 66% of your measurements to fall in this area, 94 in this area, and almost 100% to be in there for a measurement system that's in control. And this is from standard methods for the analysis of water and wastewater. And this talks a little, this chart basically breaks down interpretation of these Schuhart charts. First of all, this is just the top half of a control chart. So it could be a range chart, but it could also be the top half of a 1, 2, and 3 standard deviation chart. And that's indicated over here. It used to be that we just look for those points that were out of control. But now in terms of analyzing bias, here we have a repeat analysis where both are above 3 standard deviations. That's definitely a system that's out of control. The measurement is not precise, the measurement is not accurate, and all the unknowns that we would report from a run like that really ought to be rerun after the system that's being used for measurement is troubleshot to find out where this erratic performance is coming from. In this next one, we have 3 out of 4 successive measurements that are above the warning limit. Again, we're tending away from the mean, the average for the analysis, so we're tending towards an area of being out of control. And we're getting 3 above the mean, which tells us that there's some bias that's starting to occur in our measurement system. Again, this would be an indication that we should start to troubleshoot the system that's doing the measurement to find out why it's moving in this direction away from a normalized distribution about the mean. In this one, 4 of 5 successive were above the 1 standard deviation level. So we're still pretty tightly about that mean, but 4 out of 5 of the points fell to one side of the mean. So there's an indication of bias. And in this situation, 8 successive analyses above the mean. We've done 8 in a row that are above the point. In order to get that mean again, we're going to have to get 8 that are below it. I mean, it ought to just be logical to see that. So we definitely have bias. The real value of this kind of thing, aside from guaranteeing the quality of the results that you give to your customer, the person that's using the data from this kind of a measurement system, is that from an analyst using this kind of a chart system, the analyst should be, and using these kinds of indications of quality, the analyst should be able to spot a problem coming before it occurs because of this tendency away from the mean, this bias away from a normalized distribution. They should see that their system is starting to go out of control. And that results, from a laboratory management standpoint, results in significant savings on repeated analysis, analyst time, delays in reporting data, and so forth. So this kind of a quality process, the Schuhart process, at this point in New York State is required for all laboratories. I believe there are some parts of the country that aren't using it yet, but the eLab system requires it. And it results in a continuous ability to improve quality within the laboratory and the ability to spot problems with quality basically before they occur. Okay, we're at about 2:50. So I have one more section that Gary and I discussed last night, and I'm going to leave it out and open the floor up for questions if anybody has any questions.
On that, you were saying that when you have trouble on the control charts, it indicates a problem in the lab analysis procedure?
It can. This is an argument. We have a team within the laboratory that works on quality processes, and we're still kind of arguing some of this because, first of all, there's an assumption made, and it's an incorrect assumption even when it's made by the best technicians in the world. And that assumption is that all we're dealing with quality control is indeterminate errors. And if we were just dealing with indeterminate errors, those errors that arise naturally don't arise from human error or mechanical error, if we were dealing with that, then you would expect to see a perfect normal distribution that could never improve. But in fact, what these tend to be are these biases moving in one direction or the other tend to be indications of determinate error coming into the process. So for example, atomic absorption spectroscopy depends on a radiant energy source, which is generally a tungsten lamp or a hollow cathode lamp, which passes a beam of light through either a flame or a colorimetric solution, and then that's picked up by a detector tube, and there's electronics associated with the front end and the back end. There's gases associated with the flame. The bias that we're starting to see in the charts could be an indication that a lamp's going bad. It could be an indication that a detector's going bad. It could be an indication of a bad lot of gas burning in the flame. Could be an indication that the prism or diffraction grating that controls the wavelength of the lamp is out of adjustment. We're never sure by looking at a quality chart what the problem is. We just know there's a problem starting to occur. At that point, it becomes incumbent on the technician and the chemists who work with the technicians to go into problem solving and see if they can, systematically approach it. What's the most likely cause? Try this, try it. But to do it before a whole lot of work is done with a system that's out of control. Whereas in the old days, it might be possible, especially when it was a calibration line that was run for a month. You did a calibration in January, you had a tube in an instrument run out in the middle of the month. You didn't find out until February. So you had 3 weeks or 2 weeks of data that was rotten quality, very poor quality. It was reported out. There was not a whole lot you could do about it at that point. Now we're trying to do quality on a daily basis. And in fact, our paradigm within the laboratory now is you run your standards, you do a quick regression, you run 2 externals at the top and bottom end of your range, you calculate those externals, and if they're not within the control limits, you stop the process right there. So no sample gets run until there's been a demonstration of linearity and accuracy. Precision we don't worry about until the run's going on, but right off the bat, we're looking for the quality of the process before we even start to get into the samples. Did I answer your question?
Yeah.
Okay.
And these were just all your standardized samples that you were showing on the chart.
Right. Well, the first chart I showed was externals. They were samples that were provided by another agency or private company, but we pay, for an external reference, you pay very good money, and they charge very good money because they guarantee that if they say there's 100 parts per billion, there's 100 plus or minus 1. That's a trust factor we have. We did run into a company that certified their material, and we just kept getting different results, and we called 4 or 5 other laboratories. They were having the same problem, and we found out nobody's perfect. So, but we then called that company and presented them with the data from 6 laboratories. They went back in, and in fact, we were able to use the data that they came up with to go back and correct. And we did spend a fair amount of money trying to correct the problem, which wasn't ours there, but we were at least aware that there may have been a problem beforehand, and 20 years ago, that kind of tracking wasn't done. The second one is precision. The system could be very accurate, but be imprecise, and that we run replicates, but we track those replicates the same way. And the other thing that we do, I didn't really mention this, but we are working over time. The control chart that's generated in January 4 years ago had better have much wider limits than the control chart that was generated this year, or our quality's getting poorer every year. We're trying to bring those limits closer and closer so that we are at the limit of determinate, indeterminate error, so that all we're looking at in a control chart is that indeterminate error that we really have no control over.
When you do the regression, do you have a constant term in the regression, or is it a regression to the mean, or to the origin?
No, the regression is not forced to the origin, because Beer's law says that there will be deviation, that the linear relationship does not necessarily go to the origin, and it's not linear to the origin. It might not even be linear as you approach zero concentration. So we allow the line, the intercept is calculated, and that intercept is then used as part of calculating your concentrations.
Another question. When you say dilute things and that increases the variance or something, how do you use that? Or qualitatively, what's going on there?
Well, every time you do an operation to a substance, you introduce a possibility of error. Normal method for dilution is you take a volumetric flask, and so I take a 100 ml volumetric flask, and I take a 50 ml pipette, and I pipette 50 mils of my sample into the 100 ml flask, and then I add 50 mils of water up to the line. Well, there's an error associated with the pipette, there's an error associated with the flask, okay? So I've just increased the amount of error in my measurement. So I don't like to see somebody dilute something 1 to 100, because there's a lot of room, that one unit becomes a very small amount of the whole thing. So to me, the error associated with that from the technician has gone way up.
You don't use that in the analysis.
Oh, yes, you do. You get a 1 to 100th dilution, and you get a value back that says 20. Really, the value you have is 20 times that 100 is 2,000. But that 2,000 is plus or minus 100, not 2,000 plus or minus the 1 that you might have at 20. Your multiplication of error occurs through the dilution. There was a question in the back.
Do you use any sort of statistical vacuum such as we need to add to your control charts?
Not yet. Our control charts are done with 3 QuattroPro spreadsheets that I built, where people go in, they put their 20 points in, the standard deviations and all are calculated automatically. The series for plotting are calculated automatically. All they have to do from there is go in and adjust the scale on the graph and send it to the printer. So I haven't had a chance to look at a stat package on it. It was something that, because it took the average technician in the neighborhood of 2 hours to assemble a tally, 20 points off of 6 or 8 runs, and do the statistics and then hand plot the graph. When we got a spreadsheet in the laboratory, I said, this is a place where we can save some time. And most people can get the tally together in about a half an hour, and I can have a graph like that plotted in about 10 minutes once I've got the tally.
You start looking at all those Western Olympic rules, 2 and 3 and 4 and 5 and all that, those tricks. And then you have to just do that bang, so it's all done for you.
Well,
It's really neat, I think.
another...
You have sold in Monroe for $100?
Another thing there, though, is that we print the blank chart. So let me put this back up. And I agree. There are a couple of us, somebody for the medical examiners and myself, have both been looking at running in the computer, where we go to the computer and look at it. But we're required by law to have a hard copy available if an inspector comes on site with the data plotted in real time. Now, the cost to print a new graph every time 4 points get added to it and then put it into the book becomes pretty expensive. Secondly, if we let there's certain things that if you let the computer do it, yes, it's easier, but the best computer we have in the laboratory is the one between the ears. And that's why we pay people good money. The whole point of this, and the analogy that I use for people, is that this is the headlights on a car driving down a road at night. We have no idea what the concentration in what we're looking at is, of these substances. The only thing that gives us any idea that we're accurate, that we're on the road, is quality control. So our goal and our process over the last 6 years has been to take technicians who originally viewed statistics as an albatross they had to wear around their neck, and get them to embrace this process and see that this process is the only thing that really allows them to go to sleep at night feeling confident in the work that they do. So it's, to our way of thinking, having the individual plot these points by pencil is much more valuable than having the individual pop them in a computer and maybe never look at the chart again. Because each time they plot the points, they're looking at the trend. They're looking for the trend. And that's where the tool is valuable. Now, we are looking at using the computer to plot long-term and to accumulate all the data. We can do that as it stands. The medical examiners use an Excel. We're using QuattroPro, and we're probably going to Excel. $100 is inexpensive for software, but I don't have it. In my budget, I can't get it, so we're using what we have. Yes?
Two questions for you. First of all, you said you use the external standards.
Right.
Do you use it from just one company, or do you use it from two companies?
Actually, we've used them from as many as 4 different sources, and we've also made some internally at one point. What we're trying to do now is we've got one company that's been real good. We work theirs. And we're also using, now the other part of my presentation that I didn't really get into, it gets very in-depth, is a third facet of quality is inter-laboratory comparison quality. We participate in round-robin monitoring which involve as many as 130 other laboratories with the State Health Department Environmental Laboratory Approval Program, with the United States Geological Survey, Surface Water SWRS, which is their quality program out of Denver, Colorado, and with the Canadian, it was Long Range Transport of Atmospheric Pollution's LRTAP. And the name has been changed, and I can't remember what it is at this point, but it's an excellent quality improvement program for laboratories. Includes about 130 American and Canadian laboratories. And what we do now also is obtain the samples that they send out for analysis. We obtain aliquots of those samples and run those as externals once the results of the interlaboratory comparisons have been released. So we're using as many different substances as we can. But we require that we run, because of what I showed, the first thing, the deviations in the low and high ends of a standard curve due to Beer's law, we want to see externals run in the region of the low end and the region of the high end. The middle is easy to anchor, but those two areas, to see that our accuracy is good in those two areas. But we get as many different materials as we can. Your second question.
It had to do with the spectrometry that you're doing. Do you use only atomic absorption, or do you use light spectrophotometry?
Well, yeah, we use light spectrophotometry or colorimetry. I mention atomic absorption because that's the one that Beer's law is most normally talked about. But these relationships, regression type relationships, also exist in chromatography, which has nothing to do with absorption of light, which has to do with basically anywhere where you can measure a known substance and then measure an unknown and compare it, you're going to use regression for it. About the only place where we don't use it is gravimetric analysis, which is weighing things, where it's straight out weighing, and titrations. Titrations don't require it, but virtually everything else in the laboratory, we use regression for generating results.
I was just wondering why you took the voltage readings instead of just direct absorbance, but if you're doing atomic absorption.
Well, the one that I showed here was actually a colorimetric analysis. It's a Technicon auto-analyzer system, so it was designed in the 50s. It feeds a strip chart recorder. We have a total organic carbon analyzer that feeds a digital integrator, gives us a result. We don't like the result. We do another regression on it. So we're doing a second order regression then. Another function of government in the United States is you can't depreciate anything, so we're using equipment that industry got rid of. You know, they depreciated it, got rid of it, we bought it at a good price. So a lot of the equipment we work with, we can't interface to a computer because it doesn't have the ability. But as we replace equipment, we're looking for that capability of running it to a digital integrator and into a computer so that we can eliminate a lot of the manual calculation parts. But we still want people to understand what's going on with it. You know, and when I started working there 10 years ago, there were some analysis where we worked with calibration curves. They were still using calibration curves 10 years ago. Conductivity was run with a calibration curve. Conductivity at this point in a brand new system, you'll get all your results directly from the measuring system. All the integration and everything are done for you. But we're at least not using a Wheatstone bridge anymore. So, any other questions?
The curve you got for Beer's law, is the linear part that actually, does that pass through origin, or because you want to expect some sort of absorption even at zero concentration?
Right, but what happens with most measuring systems is that the system itself produces noise, and it becomes, do you understand? And by noise, I don't mean necessarily audible noise, but if you have a pen that's being moved by a voltage, if there's nothing at all going on, it'll be moving a certain amount. As you approach zero, the amount of absorption of light or the amount that you're measuring can't be differentiated from that sort of static being created in the measurement system. So that becomes the level of detection of the system. And to get into a discussion of the other factors in Beer's law that cause it to the deviation from linearity, ionization and so forth, that's a little more chemistry, a little less statistics, and I didn't want to get into that here. Getting into the more advanced statistics in terms of the interlaboratory, we kind of talked about that yesterday as maybe, but probably not, because it was much more rigorous than what we needed for this.
I was just wondering in terms of whether a logarithm transformation would be more appropriate for regression.
A what?
Because it seems that the amount of error you expect increases more or less proportionally with the size of what you're measuring, yes?
Yeah, but
which often means logarithm transformation or regression.
oh, all right, log treatment. Actually, there are some analysis, arsenic especially, where either log treatment or exponential treatment are done. And in bacteriology, virtually any of this kind of work that's done in bacteriology will be log treated before the work is done. So there are exceptions to that, and there are higher order regression. There are analysis that don't follow Beer's law but do follow higher order regression kinds of things, and where it is done. But for the most part, what we're looking for is that linear region to work in.
If you do a logarithm transformation on both axes, then look at the offset rather than slope.
I didn't hear.
If you take logs of both variables and look at the offset rather than the slope, that would give you measuring the same thing, but you'd be getting more uniform variation.
I agree with you to an extent. Nevertheless, from talking, for example, to Keith Long from Denver, another thing that we've done is break the line into regions, what we call bracketing. They're not considered within the realm of chemistry to be valid techniques in a lot of cases. I mean, and again, it gets more rigorous than what we were really looking to do here, but there are some pretty detailed justifications for the use of the regression in the areas where it's used. But there are also I've seen some pretty valid reasons for not, for not doing some of what you're talking about. But I don't have the material with me in terms of that. Gary's indicating to me that I should wrap up. And I'm on the spot, so.
Thank you very much for that.
You're welcome.